So I wanted to talk about a problem that is, I think people are starting to recognize it as being more and more important. And there's a number of different aspects to this particular problem. And I think I'm going to stick to one of them, but there are a couple of issues with memory efficiency within our applications. And, just recently I just had a conversation with one of the founders of one of the larger cloud providers, no, not the Microsoft one. And, he was talking about, doing strange things with the Java virtual machine just to help try to solve this particular memory for their customers. I think, there's Alibaba, I know, has been involved with JVM development for a couple of years, for a number of years now. I mean, they're looking at primarily memory, and what can we do to reduce costs and reduce memory footprints and deal with things like that. And I know that we've been working with a very large organization, which I'll remain nameless, but their problem is what we call densification. And we look at some of the problems, like we're looking at one now. And the problem that they're having, the thing that's keeping them from densification or really making full advantage of it, is the memory efficiency of their Java applications. And so I just wanted to address that situation. We already done that, so we can just go in that and take a look at the problem. So I guess I'm supposed to start with a demo. And to that end, let me bring some code over here so we can all look at code. And run. I'm assuming that everybody can see that. So I just have this application, and we're just looking at it. It's just a simple little thing. What it does is that you guess, what you do is you pick a number, or three numbers between 1 and 100,000. It's like a lottery type thing, and you hide it. And what this application is going to do is it's just going to say, okay, what is that number? And here it's saying, like, okay, well, I've made this guess, and I'm going to score it. And I'm going to say that, I got one of the numbers right, and it's in the right position. And that's all the information I have. So it's using this information to filter its guesses and try to refine until it gets to an answer. Now, if you look at this thing, oops, I got controls in the way. If I just look at the tool in here, you can see that I'm pretty much running CPU hot here. Why is it only running one? No, it's running all cores. And I got the webinar software running here, so that's interfering and things like that. But besides the point, this thing is basically all fired up. And the question is, okay, what can I do to make this faster? Well, to understand what I need to do to make this faster, I have to understand what the underlying performance issue is in this particular application. So I'm not going to wait till completion here because it takes a while. I'm just going to continue to run that application in the background. We can see the time. Probably under these conditions is going to be closer to 3 minutes to run, right? So, and this is a question I ask people, and and normally in a nice room, and I can get people to raise their hands and say, what is your performance trouble spot? What is your performance trouble spot? And really, if you think about it, I'm going to suggest that, most people don't know. You might have some guesses and things like that. And I'll back that up with this particular survey over here. So I'm going to get rid of this. Okay. If we look at the survey, this was done by Rebel Labs a couple of years ago, and I think they did a really good job. It's a very nice survey. So there's nothing wrong with the survey. But what they did was they asked this question to their audience, and they said, what are the typical root causes of your performance issues? And this is what they showed up. This is what showed up, right? And you can see it's the typical suspects are up there. All the things that you would expect to be a problem are there. So the question is, you know, what are they missing? Well, what they're missing is this little one down in the corner. In our estimation, this problem exists in about, 60 some odd % of all of the applications we encounter. And we get data from applications like all over the place. People send me data. Now, the problem is, and this is how it ties back into memory footprint, is that when I go to tune an application, one of the things that I have to consider is what is your memory churn rate in the application? Because that dictates how I'm going to tune the nursery, because that's going to dictate how I'm going to calm the garbage collector down so that the garbage collector is not as a heavy interference. Like, I'll just tell you the last GC log I looked at, the garbage collector was responsible for 33% of the application runtime. And why? It's because their nursery was undersized, right? And their allocation rates were around 4 gigabytes per second. In order to accommodate a 4 gigabyte per second allocation rate, you need minimally about 16 gigs of nursery. They had given this application 1. And because they'd only given them 1, and they starved the application for memory, the garbage collector had to work extra hard, and extra hard means you have extra long pause times. So this is a huge problem, and it actually prevents you from meeting a lot of your performance goals. And sometimes it's fairly easily solved. I'm saying, well, in this one I'm claiming about 70%. So 67% doesn't matter. It's a huge percentage. And is the garbage collector at fault? No, it's not. It's doing its best to try to keep up with this. As you can see, the problem is really algorithmic within your application. And it's not just you. It's, the question is, do you use Spring Boot, Cassandra, or any other NoSQL? I guess Hadoop can go in there. We can name a whole bunch of others. Apache Spark again, or any big data framework, Log4j, or any Java logging framework. Let's not pick on anyone in particular here, right? Do you use a lot of JSON? Here's an interesting problem we're running into with a number of clients now. It's like, do you actually use off-heap data structures? Ecom caching products, Hibernate, and so on, and so on, and so on, and so on, and right? So if you're using any of these things, and you're very likely in the 70%, we see excessive logging as being an issue in a large percentage of that 60 to 70% of the applications that we actually run into, and we can actually get a picture as to what's really going on. It's just how people are logging is the issue. And a lot of it is like unguarded. So there's a lot of things that just happen, just silly little things that accumulate. And all of a sudden you have a hot allocating thread. And here's where it gets really interesting. Given the current memory bandwidth that you can see on the back end of the chip, writing this data out to memory, you can have a single hot allocating thread actually take down an entire socket. And what that's going to do is it's going to stuff up the back end of the chip. In order to accommodate that, the chip itself has to slow down everything else. And notice I'm talking about the chip, not your application. And because what that means is, since it slowed the chip down, that means that everything else running on that chip is also slowed down. So if you have multiple containers with multiple things running on that same socket, or set of sockets. Now you can see the problem is like, it's not just affecting me, it's affecting everything else around me. So this is another source of noisy neighbors. And the bigger issue here is that it's mostly invisible. If we go back to the chart, you have to ask the question, why are only 10% of the people complaining about excessive memory churn when we're seeing this as a problem just about everywhere we go in a vast majority of the applications that we look at? And the answer is observability. This is something that people are simply not looking for. So this is a bias in our tools. Everyone expects the database transactions to be slow. Everybody expects the interaction with the database to be slow. And generally, in most systems, it really isn't. Databases are quite fast and they scale quite well, right? But since we've traditionally had that problem, we have a lot of instrumentation around that problem, and the instrumentation is lighting up on the database all the time, so therefore we think, our database is slow. But that's just a bias in how we're taking the measurements in our systems. If we start removing the bias from our measurements, then all of a sudden this picture changes quite considerably, and you start seeing the importance of the memory churn issue. Right. So, and just how big is the problem, right? We reduced allocation rates from 1.8 gigabytes per second. This is a framework we use that it's for financial product markup language. Right? TPS jumped from 400,000 TPS to 25 million. The other issue is that when we start taking the pressure off here, we're not getting percentages of speed up in the application. We're getting integer multiples of speed up. Right? Stripped out of the logging framework of the transactional engine. And this was done actually in the Netherlands, quite close to Amsterdam. And we get a throughput jump of 4x. There's WebSocket framework, because we're working with a product company, right? Reduced memory churn by a factor of 2 and increased throughput. And that led to some other very interesting benchmarks and stuff like that. So, and the stories go on and on and on. We can add to it by saying, like, we can actually reduce footprint in this application, which results in, like, I think we're estimating a 25% reduction in the number of servers that a company has to use in order to support their load. So you can see these numbers get really significant, and they have really significant impacts. So really what's going on in this whole situation? Well, what we're looking for is code that's doing this. It's just allocating a lot. It's hitting these allocation hotspots in our code, right? So, when we allocate in Java heap, we're going to allocate on a couple of different paths, right? And what we're hoping for is that the small objects are going to be optimized into what's known as a scalar allocation, which means that allocation is going to basically be inlined into the code, right? So, what are the cases when we can do that? Well, we can do that when we know that the object being created is small, generally only contains primitive values, and is not going to escape. And that gets into another piece of analysis that the JIT compilers do inside of your application. They're going to look at the data and say, okay, does it meet this criteria? Is it small? And is it only going to be visible by the thread that has created it? If it's only visible by the thread that's created it, it's probably going to be able to rip that thing apart and scalar allocate it, which means it's not going to be allocated on the heap. And that's just a different operation, and it actually takes pressure off of the heap. But if you can't do that for whatever reason, if it fails that test, then you're on one of these other paths, which means you're going to be allocating out in the heap. Let's go time 6 and 7. I'm completely lost for time, so I'm happy to take cues on this whole thing. So what's the issue here? Well, it's really when we're looking at the each of the individual allocations, they are cheap. They don't really cost you a lot. But if you get into a hot allocating loop or hot allocating path and stuff like that, the problem is going to be frequency. And anything that you do that's cheap, but you do it a lot, then of course that's going to be expensive over time, right? And so the allocation rate is going to be an approximation of the allocation frequency, right? What we can do is we can look at a GC log, and we can use that to give us an approximate value for what the allocation rate is. But what's going to, but that doesn't really give us the allocation frequency. But what we can do is just infer that. So we're going to infer the allocation frequency as what I call a proxy measure. So I can't get at that directly, but I can actually get to it by looking at just how many bytes are allocated. But it's really not the bytes that are the problem, because if I ask for 100 bytes or ask for a megabyte, it's going to be approximately the same cost. I think I can run through that right here just to see what's going on. I mean, prior to that, I was talking about the nursery, right? So this is an approximation of what our collectors face. I know the details differ for each of the collectors, but this is approximately what's going on. So I have this marked as Eden. That's really our nursery, right? So if we actually look what happens in here, we can see that when we execute some piece of code, we're gonna have this top of heap pointer. So we're gonna have thread 1 actually do this allocation here. And you can see it's gonna create a new foo, and then afterwards it's gonna create this big byte array. All right, so if we execute this particular piece of code, what I'm going to do is I'm going to go out into the heap and I'm going to say, okay, I need enough memory, a buffer big enough to support this allocation of foo. Now, they've optimized this in the sense that I'm not just going to go out and get the 10 or 20 or 100 bytes that I need to allocate foo. I'm going to go out and get what's known as a thread local allocation block. So I'm going to go out and get a megabyte of memory, right? 1 meg. And once I've gotten that 1 meg, then that's dedicated to allocations made by thread 1. So when thread 2 starts allocating, it's going to do the same thing. It's going to go get its own TLAB, and it's going to start allocating into that particular TLAB. So what that does is it reduces contention on this thing which we call top of heap pointer, right? So we're going to have a TLAB pointer instead. And we're going to do bump and run. So this is why the allocations are so cheap. To allocate foo, all I need to do is bump that pointer. It's a very quick operation. And then I can just fill in the data, right, into the slot. And as I keep allocating, of course, I'm just going to keep bumping that pointer up until I hit the end of the TLAB. And when I hit the end of the TLAB, then I can go back into the heap and I can just grab another TLAB and off you go, right? So as I mentioned before, when bar 2 fires up, he's going to get his own TLAB. He's going to allocate for bar, fill in the data. If we have something that's bigger than a megabyte, then unfortunately that has to go on a slow path. So that's going to just directly bump the top of heap pointer. And of course we can allocate the data into this. So you can see that these things are happening very, very quickly. Not a lot of work being done here. So the problem isn't an individual allocation. It is all of your allocations in aggregate. Tenured space works slightly different, but generally we don't have to be so concerned about allocations in tenured space because it's generally the garbage collectors that are going to be allocating into the tenured space, not our application threads. Under rare conditions, the application threads will allocate directly into tenured, but that's generally what's not happening. So Um, as I mentioned before, with high memory churn rates, we're going to quickly fill Eden, and that's going to increase the activity of the garbage collection. And it has all of these knock-on effects. It's going to speed up aging. So how we move data through the different memory spaces is determined by the number of garbage collections they survive. So think of it this way. If I have a piece of data that I know that I'm going to keep in memory for 2 minutes, for whatever reason, it's there for 2 minutes. The question is that going to be in young generational space where collecting it is going to be really cheap, or is that going to be in tenured space? The answer is, well, it depends on the frequency of the garbage collection. So I don't know, right? And this gets into this question where we end up experiencing premature promotion, and that puts a lot more pressure on the garbage collector also. So you can see that by increasing the allocation rate, what we're doing is we're causing the garbage collectors to have to work harder. And because they work harder, there's all of these extra costs that are incurred by the garbage collector. So quite often what happens is that the garbage collector gets blamed for the problem here, because it's the garbage collector that is exposing the problem. But it's really not the garbage collector's fault. And you really can't tune the garbage collector. You can tune the garbage collector to hide this problem, but the cost of tuning the garbage collector is going to be that I need a lot bigger footprint in order to manage this problem, right? So really the problem that we want to solve is how do we find the hot allocators, and then basically algorithmically fiddling around with that piece of code to try to see if we can quiesce, like not allocate and not go through as much churn. What are we doing for time?
Another, I think 15 minutes.
15?
Or 25. I'm.
Oh, 25. Okay. Yeah. So I was looking at it because
15 minutes. 15
yeah, I haven't done the time conversion in my head and stuff like that. So here's some charts that I think that draw this out. So if you look at the chart on the left-hand side, basically what we're looking at is heap occupancy. And the black line at the top is actually the size of heap. So you see that the Java application in this case is resizing heap. And but anyways, the point is, like, if you look at the bottom of the chart, and you can see that red line looking, that's the heap occupancy. And if you look at the GC pause time, you can see that it's just completely correlated to how much live data that you have, right? And the other aspect of this whole thing is that, of course, if I have this higher rate of churn and I get things promoted into tenured and all of this activity is happening, then my live set is going to be larger, because I'm going to be retaining what's known as transient data for longer and longer periods of time. And that's going to contribute to the size of the live set, which means my pause times go up. So you can see there's just so many bad things going on here because of this. So let's go back to this particular chart here. And, so we're going to, so the question would be, so what is the effect here, or what does an optimal allocation rate look like? And really the answer is, well, from my mind, it seems to follow this power curve from our observations in the wild. And you can see that the red zone is anything really above 1 gig per second. And this is a bit of an arbitrary number, so this is not really scientifically derived. It's just been derived by our work on applications in the field. But as you can see, the power curve really drops fairly quickly, above 1 gig per second, in terms of what the size of the performance gain is that you can get. And if, by the time we get down to around 500 megabytes per second, 300 megabytes per second, then there's likely very little gain left that you can get. So one of the things we actually want to measure in the application is, like, what is the allocation rate, and let's use that information to guide our tuning regime. So, you know, with that note, let's go back to our application. Let's see how long. Yeah, so it took 151 seconds to run. And so the question is, okay, you know, what's the issue with this problem? So I guess you can probably all guess. It probably is suffering from high allocation rates. So let's confirm that. So I'm going to bring up our log analysis tool. Unfortunately, right now it's behind Microsoft's firewall, but we're hoping that it's going to be open sourced very shortly. So we're going through the processes that we need in order to open source software. And then Sensen would be available in the wild again. So you can see as I go through this GC log here, let's straighten this out and make it look a little better. You know, not much memory being used here. So all of that looks really good. If I look at the allocation rates, you can see that's an outlier. I'm not going to worry about that one. There's some funny maths that happen here that sometimes make our estimates really weird. But if we look, we're running at about 6.5 gigabytes per second. Now, oddly enough, this value on different pieces of hardware might alter a bit, but having bigger, badder, faster servers isn't really going to help you here. They're all going to top out at approximately the same allocation rates. You're not going to be able to push things faster. And there's reasons for that. It's because the write channels writing back to memory are all tied to memory chip speed, not CPU speed. And the memory chip speed and the bus to feed the memory should be synced at approximately the same clock rates. Those are pretty much the same no matter which piece of hardware you're running on. And that's why this value is capped at the levels that we see it. And so we can take this data off of, you know, all kinds of different pieces of hardware, and you're going to find that the capping is approximately the same. Here it's typically about 8 gigs per second. I'm guessing it's a bit lower because of, you know, all of the extra things that are going on this particular machine. Okay, anyway, so we know that we have this problem here, which is high allocation rate. The next question is, you know, what can we do to actually diagnose this? Well, probably the best thing to do is to bring a profiler in to the table. So I'm just going to go to use this Visual VM tool. There's all kinds of tools that can do this job. This is just one that I have here and now. It's free. You might say flight recorder. Could I do this with flight recorder? And the answer is yes. You can actually find hot allocation sites with flight recorder. It's a little better with the newer version than with the older version. However, as I say that, it still lacks a bit of data that helps you identify the problem easily. So, so it's cheaper. You could possibly do this in your production environment. It has all of those advantages, but the amount of data that it gives you to help you characterize the problem is not quite as robust as what you get from another profiler. Now, the other issue is, and I can show you this in a second, is that, so I'm just going to set up this thing to profile this while I'm babbling on, I guess. Oh, right, sorry. I keep forgetting. You can't see what I can see, right? So let's, so what I did was I just set up the memory profiler to profile for everything since I don't know what's going on. And I just click this particular button here to attach the profiler to the application. And now what I'm going to do is I'm going to say, since frequency is a problem, I don't really have a frequency measure here. But what I do have is allocated object count. So I'm going to use this as a proxy for frequency. So I'm going to just sort here, and I'm going to say, okay, so what's my most frequently allocated object? Because that's going to be my hot allocator. So I can go back to the application here, and I can just run it. Oops, let's push it over here. Just push it over here so maybe we can see what's the green bar should go to done. And then we can just watch it. And I think quite quickly, well, this is really easy now, right? We just look for the thing at the top of the list. Well, the reality is it's not quite this easy, right? I would just point out this application runs bimodally, and what I mean by bimodal is that, oh, okay, it's sort of in a guessing position right now. It seems seemingly running fast for some reason. Okay, it's running bimodally. It's like when it's making guesses, it takes one execution path, and when it's not making guesses, like I mean, as in trying to score the guesses, it's taking another execution path, and each mode of this application is going to have one allocation hotspot. Now, the odd thing here is that, you know, this allocation hotspot is a real allocation hotspot in this application, right? And we can drill down and we can actually see the source of this allocation hotspot here. Actually, I'm going to do this in a snapshot because it's going to be stable. Right? And you can see that, you know, here we are, we're actually looking at allocation code. So this is the type of information that's missing from Flight Recorder. In other words, it'll tell you that, okay, I got this problem with int array that's causing a lot of memory pressure, but it really doesn't give you the information to say, okay, where is the allocation hotspot actually existing in the code? So it just doesn't collect that information. But anyways, we can use this to actually say, okay, well, I obviously want to go into this class here and say, okay, what the heck am I doing here that's causing me to allocate all of these int arrays? Now, as I mentioned, this application is bimodal, and being bimodal, what it does is it means that there's another allocation hotspot that shows up, but it only shows up when I'm pushing guesses onto the screen. So I know what that is, so I'll just tell you because I'm not going to go through the whole run, or maybe it's popped up by now. Let's take a look and see what's going on here. No, it actually hasn't popped out of the noise floor here yet. So I'll just go back to the snapshot and just say it's this one right here. Now, this is where Flight Recorder does have an advantage over most of the other profilers, in the sense that this looks like a hot allocator to the profiler. And if we go back and look at the code, we can actually find this thing here. Okay, so here's the code. So we're checking, is the thing that I'm passing, is that a solution? So I'm going to go over all the board entries, and I'm going to score it against the board entries. And oops, that's interesting. Okay, so I'm going to score it against the board entries, and if it scores well, then I'm going to say, okay, go test this thing and say, okay, this is a possible solution, right? And so I'm going to just basically say, okay, how good was my guess? And this is going to be a measure of goodness. But you can see what I have here is I got this while loop, and in the while loop, I'm actually allocating the score object over and over and over and over again. And as you can see, that's probably going like, okay, that's just a crazy thing to do. Why am I doing that? That's just a hot allocator. And of course, this is just a simulation of things that happen. So I'm going to go into the score object and say, okay, well, I got this jackpot and so basically I have two ints and a jackpot. And so if I look at how escape analysis is going to treat this and how the optimizer is actually going to treat this, what I'm going to see is that, okay, this particular allocation is local to this block of code, meaning it's local to this method, which means that the thread that's creating it is the only thread that can access it. So this actually passes escape analysis. And if I also look at it and saying like, well, okay, there's 2 ints and okay, fantastic. I'm going to scalar replace this allocation. So this allocation doesn't actually happen on the heap, which means I can go and change this code and do the sensible thing, which is like, okay, let's place this out here. And I can just going to go, clear the values, make it usable for the next iteration and stuff like that. So you might think, okay, now I've removed that hot allocator from the loop and I should get a performance boost. And the answer is no, I'm not. Because the optimizer's already done this for me. Okay, but if we get back to the int array in the arrangement group, you can see that this code is really ugly. Here's the problem that the profiler is actually pointing to, where I'm just creating new arrays very, very frequently and stuff like that, right? This array eventually is being passed back, and because of it's leaving the context of this method, it would fail escape analysis, but it's an array, so it's going to fail based on that. So in this case, I'm forced to do this allocation on heap. So, you know, the next thing I'm going to do is I'm going to go and look at, okay, well, the calculate index was the next method in the call stack. So I'm just going to run through this code here and algorithmically look at it and say, okay, what is the stupid thing I'm doing here? And then make the fix. And once I make the fix and take this thing out, then this code will start running a lot faster. As a matter of fact, if I do this work and run it, it should run in about, it should be completed in about, let's just comment out this bit here. We should get about a 2x improvement in performance just by changing this algorithm. So what I've done is I've gone to something that says, okay, don't create that array so frequently. In other words, that whole method is now completely missing from this.